Hi, welcome to the video solution for physics, past paper solution. It is Edexcel Physics Unit 1, January 2005, Part 3. So let's start. Question number 17. The diagram shows a swimmer. The swimmer exerts an average horizontal backward force of 65 Newton on the water during each stroke. The length of each stroke is 1.4 meter. Show that the work done by the swimmer on the water during each stroke is about 90 joules. So you need to find the work done. It's a horizontal motion. Force is applied horizontally. So you have a straightforward question, and solution is work done is force into distance. So force is 65 Newton, distance is 1.4. So 65 times 1.4. So answer will be 91 joule. This is the work done during one stroke. The stroke rate of the swimmer is 55 strokes per minute. Okay. Calculate the power developed by the swimmer's arm. Power is energy per unit time or work done per unit time. Okay, so the work done that the swimmer is doing is just not for one stroke. It will be for 55 strokes. So the total work done would be 91, which is the work done for one stroke times 55, so total work, and per unit time, and it is a minute. T is 60 seconds, and if you solve this, you have 83.42. That means power is equal to 83.4 watt. An investigation was carried out on the drag forces acting on the swimmers. The swimmer pushed off from the side of the pool with his arm straight ahead of him, and his velocity was measured as he glided through the water. This was repeated with the swimmer's arms at his sides. So we have a two different situation of glide. After pushing, swimmer glide placing arm in front, and the glide 2 is arms on the side. The velocity time graph was plotted for both glides. Glide 1 is solid and dotted line is glide 2. So velocity and time graph. Okay. Use the graph to describe and explain the motion of the swimmer when performing glide 1 and glide 2. So these are the situation for glide 1 and glide 2, and this is the graph. So if you see, in both cases, during the motion, velocity is decreasing, and the reason of decrease of this velocity is acting of the drag force. So due to drag force, velocity decreases for the both glides, and as the velocity is decreasing, so as time passes, or due to decrease in the velocity, drag force also decreases. Moreover, because of the large cross-sectional area of the glide during the performance of glide 2, swimmers will experience greater drag force. So the rate of decrease of velocity of during the glide 2 will be greater than the glide 1. So you can summarize all these points as this. In both cases, velocity of the swimmer. Yeah, okay. You wish, if you wish, you can add this point that because of the large drag during glide 2, so the velocity of during the glide 2 decreasing with the greater rate because of the large drag force. The drag force can be calculated using drag force is equal to half of C rho AV square, where C is the drag coefficient, rho is density of water, A cross-sectional area of the swimmer, V velocity of the swimmer, demonstrate the drag coefficient is a quantity with no unit. So we need to show that the drag coefficient C has no unit. And how do we do that? First of all, we need to make C as a subject of this equation. If you do that, so C is equal to, I'm using letter F for drag force. So you say that 2F divided by rho A and V square. When we deal with the units, so we don't worry about the constant because we are dealing with the unit only. So you can say that force has a unit Newton, but it's good to write base unit of Newton in this case. So base unit of force is kg meter second minus 2. This is unit of the force, divided by rho. Rho is the density of the water. So density, unit of the density is kg meter minus 3. A is the area, that means meter square, and V is the velocity, and unit of velocity is meter second minus 1. So velocity unit is meter second minus 1, but in this case we have V square, so we have meter square second minus 2. Clearly you can see that second square and second minus 2 and second minus 2 can cancel. Kg and kg will be cancelled, and if you see, this is meter 4, and meter 4 and meter minus 3, these two combine to give you meter, and this meter will be gone. So overall all units are cancelled, so you have no unit. Or you can just simplify mathematically. If you wish, you can take all these up, changing their exponent sign, and you can add subtract the exponent. So at the end you have no units, all will be cancelled. So it's your choice. Suggest and explain an additional measure that swimmer could use to reduce the drag force acting on him. Okay, so during swimmer can wear special design suits, tight fitting suits, so that the flow around his or her body is laminar, so it will experience less resistive force. Moreover, if swimmer swim with the low speed, so due to low speed, drag force acting on the swimmer will be low, so it can reduce the drag force doing these things. In 1909, Robert Millikan did an experiment to find the charge on an electron. Tiny charged oil drops were dropped between two charge plates. So these are the charge plate and these are oil drops, and they are falling down, coming down. The radius of an oil drop had to be determined so that its weight could be calculated. Before the plates were charged, Millikan observed how long it took for an oil drop to fall through the air between two fixed points. The terminal velocity and hence the radius could then be calculated. Complete the free body diagram or free body force diagram below for an oil drops falling freely through the air. So oil drop is falling freely, falling. That means if an object falls, so the weight acts downward, upthrust acting upward, which is already given. It is falling down, so you have a drag force in upward direction. So you can say that you have weight acting down, and then you have drag force acting, these two other rest of the two forces. Make sure that when you draw the arrow, especially in case of motion of an object in a fluid, make sure that all the arrows should touch the surface of the sphere or of the object, whatever it is. Explain why the oil drops reaches the terminal velocity. So initially at t equal to 0, when drops start falling, W is greater than upthrust plus drag, and as velocity increases, so the drag force also increases, and the time comes when weight equals upthrust plus drag, so no net force, that means acceleration becomes 0 and velocity remains same. It is called a terminal velocity. An oil drop is traveling at a terminal velocity. The oil drop takes 11.9 seconds to fall at distance of 10.2 millimeter. Show that the terminal velocity. So oil drop is traveling terminal velocity. That means it's a steady speed or a constant speed. That means we can use S is equal to ut. So u is the velocity and distance upon time, and distance traveled is 10.2 into 10 to the power minus 3 because of this milli, divided by time is 11.9 seconds. When you solve this, you have answer 8.57 into 10 to the power minus 4 meter second inverse. You can round this off to 0.001 meter second inverse. So this is your velocity. Assuming that upthrust is negligible, show that the radius of the oil drop is about 3 micrometer. Density of the oil is 920 kg meter minus 3. Viscosity of air is 1.82 10 to the power minus 5. So if you see, during the motion of the oil drop with the terminal velocity, you have equation W, weight of the oil drop, is equal to upthrust plus drag, but they are saying upthrust is negligible. If upthrust is negligible, you can ignore upthrust. So your final equation becomes W is equal to D. So W is the weight of the oil drop, D is the drag force. So you can write W as mass into G. So M is the mass of the oil drop. D is the drag force, 6 pi eta R V. But we don't have mass of the oil drop. This mass can be replaced with rho into V into G is equal to 6 pi eta R V. Again, I'm explaining in detail just so you can understand. So remember all the terms. Rho is the density of the oil drop, which is this. V is the volume of the oil drop. G acceleration due to gravity. Eta is viscosity of the medium in which the oil drop is moving, in this case air. This is eta, this is rho. R is the radius need to be found. V is the terminal velocity we have found in the previous part. So you can substitute all the value like this. So rho is 920. V, I don't have V, so I can say 4 upon 3 because it is spherical. So volume of the oil drop is 4/3 of pi r cube into G. G is 9.81 equal 6 pi eta. Eta is viscosity of the air. So 1.82 10 to the power minus 5. R need to be found. V is the velocity, and we have found velocity in the previous part, which is 8.5 into 10 to the power minus 4. Clearly you can see that pi gets cancelled. 1r and 1r is cancelled from here, and you can make r square from here, r square as a subject, and then send all the number on the other side and then take the square root of r. Finally you have radius around r is equal to 2.79 10 to the power minus 6 meter, and it is around 3 micrometer. 10 to the power minus 6 is a micro. It is very difficult to measure the radius of such an oil drop directly. Suggest why? Because the size or volume of the oil drop is very small, so we don't have a mean, or we don't have equipment which can or that can measure such a small oil drop because of the low precision. And low precision means the low precision of the devices. We don't have a very large precision instrument to measure the size or diameter of the sphere. And moreover, because it's oil drop, so it can change the shape during the measurement. Explain why it is necessary for Millikan to maintain the air between the plates at a constant temperature. Because if temperature changes, that causes viscosity to change, and if viscosity is changing, then drag force is going to change. So we cannot apply Stokes law, or we cannot use the equation that we used in the previous part. So it is necessary to maintain the temperature between the plates so the viscosity remains constant, so the drag force. A student tried to model Millikan's model for finding the radius of the oil drop. The student dropped a ball bearing and recorded the time it took to pass between two light gates a known distance apart. Explain why this is not a good model for Millikan's method. The reason is the student is dropping ball between the two light gates, and the ball is moving through the air, while Stokes law is applied only for laminar flow. In the case of the student's model, flow is not laminar, and the ball, of course, it is moving through the air, so ball will not reach the terminal velocity. So it's not a best model to depict the Millikan's experiment. Thank you very much. Hope you enjoy it. Have a nice time.